this is a pretty good class. I'm really glad to see all of these people here. I see all of you have seen on the syllabus that the class is actually an in-person class. There, I think, was a certain amount of confusion. There is, I think, a contingent or a cohort who hoped that they would be able to take this course entirely online, but that's no longer the case. Things are now, the expectation for these courses now is that you are here in person, and that's going to be the expectation that's maintained throughout this course. So, so awesome. Thank you for coming. I should probably amplify. See how we do here. See if the battery's dead. Testing. Can you hear me in the back? I assume so. If you couldn't hear me in the back before, now's your best chance. So, so, welcome. This is Computer Science 1XC3, which happens to be my favorite course, actually. This is a course on Linux skills and C programming. This is a harder course than 1MD3. C programming itself is harder than programming in Python for various reasons that I'm sure we'll get into. And Linux, knowing how to use Linux is, it's a skill, and you guys are going to work on that skill in this class. This course is done in the experiential paradigm. So what that means is that we have a reduced amount of lecture. We only have 2 hours of lecture per week. Because this is a summer course, it's like 2 regular semester weeks per single week of this course, right? So per week we actually have 4 hours of lecture, Mondays and Wednesdays. But you have a whopping 8 hours of lab work a week in this class. And we do our best to try to write the lab procedures so that it actually takes you most of that time, because otherwise, why would you even bother coming in? Aside from the fact that if you don't come in person to the labs, you don't get marks. Boom. So, I am Nicholas Moore, but I expect most of you have probably had me in 1MD3. Still on. How many people haven't? Any transfers from the engineering program? Where are you from?
Engineering.
Engineering?
Engineering.
Engineers?
Mathematics.
Yeah?
Math.
Cool. All right. And the rest of you, how many comp sci people here? How many science people here? Any economists in the crowd? Any health science majors? Sociologists? Classics studies majors? No? Okay. That last one was a long shot. So, we're going to have fun. This is the stuff that you learn in this class will transform you from a pathetic weakling when it comes to computer science into the most buff Chad that you could possibly imagine. This is what we're going to do to you in the course of 7 weeks. It's not going to be pleasant, but by the time you're finished, you will be a computer person, I promise you, if you pass. If you don't pass, then you've failed to become a computer person. So, in due course. For today, we're going to run through the syllabus. We're going to then talk about what it means to be an operating system. And then we'll resume Wednesday and we'll talk, I think, about subversion control. Let me see, yep. Tomorrow, our Wednesday is version control, so. Right, so. Administrative details. These are the important websites, right? The last offering of this course was entirely online because, you know. So previously, if you want to grab like the archive of lectures of this class from previously, if you want to jump ahead in the class and take a look at what's going to happen, that sort of thing, please feel free to visit the following YouTube channel. You'll find all of past lectures there. In addition, all of the lectures for this semester are going to be video recorded, as is currently happening, and I will be posting those to the YouTube channel after the, you know, at some point the day the lecture occurs, if not the next day, sort of thing. So if you want to watch a lecture through again to, you know, reinforce a concept, or if you have to miss a class, that sort of thing, then there you go. You have access to the lectures. And you have access to the lectures on like 1.5 speed, which might even be more valuable. Avenue, obviously. Avenue is where we're going to keep the master grade book, as well as any materials which you require to complete this course. That includes copies of the slides and copies of the lab procedures. We have a Discord forum. How many people here use Discord? How many people here do not use Discord? All right, well that settles that. We have a Discord forum. That's going to be Q&A. It's probably going to be most useful to you during the assignments, as those are individual work. That's sort of not in a room with a TA. I presume that if you're in a room with a TA, you will ask the TA directly, not post to Discord, because, you know, I'd like to think that we're not caricatures of living in the modern era where we're like texting the TA when we're in the room with the TA. But anyway, Microsoft Teams, if we have to have online office hours, or if, you know, something, if like a meteor strikes campus or something and we have to put the lectures back online and YouTube fails, then Microsoft Teams will be the resource. I don't even know if I've set it up yet. And then GitHub. Assignment, management, repository. We're going to be learning quite a bit about how to use GitHub in this class. So, how many people have heard of GitHub before? Quite a few. How many people have not? Okay, so it's okay if you haven't. The whole point of this class is to teach you, right? Basically, we have a whole lecture about it, so I'm not going to get hugely in detail about it right now, but essentially, it's a little bit like cloud storage, but it also saves your project in a manner that you can recover it to previous states, and it allows the management of multiple people working on a single project in a way that makes the most sense so far. At least, you know, with respect to ways of managing people working on projects together, GitHub is the best the human race has been able to accomplish thus far, so it is prudent that we should learn it. So, I'm assuming if you're in the room, you found the lectures. I'm assuming that if you found the room, you also know where your lab sections are. We've got 3 TAs for this class, whom I have affectionately called the 3 Ryans, because we have Ryan, and Arian, and I asked him, hey, could I call you Ryan, because that would just be too good, and he said, yeah, sure. So we have the 3 Ryans. It doesn't matter which Ryan you have, they're all fantastic. Like, I'm super pleased to be working with these guys. They know their stuff really well. So what is the purpose of this course? We are going to acquire familiarity with professional software development settings and practical experience with interaction with Unix-like systems. Programming in C with documentation, testing, benchmarking, profiling, and debugging, shell interaction, and programming. Pipes and filters, revision control, all of those are labs. So we have labs on each of those subjects, although a few of them are like combined. Like testing and debugging, you sort of smack those together. But anyway, so prerequisites. You need to have taken either Comp Sci 1MD3, Engineering 1D04, although that's like the old code for whatever the first year engineering Python programming course is. Eh?
1P13.
1P13, thank you, yes. They need to update, or I need to update. Someone needs to update something, anyway. Math 1MP3, which is, I believe, their version of the same. Not as good as my course, just putting it out there. Prerequisites. So, all of these courses are courses that either teach C programming or Unix skills or both. This course is considered to be a replacement for all of these courses. In particular, a couple of years ago, this course originated out of a desire by the department to give the students of the computer science program more co-op oriented skills earlier in their degree program so that, theoretically, by their first summer break, they would have enough skills to be able to land a co-op somewhere. Now, obviously, you guys are taking it during the summer, so, but there's still, these skills, so long as you keep them up, will still serve you very well next summer if you want to apply for a co-op or, get a job or whatever it is. Presumably, you guys want to get a job. Everybody, pretty much everybody does, unless you're one of the people who doesn't. But anyway, so by the end of this course, you will have and will be expected to be able to implement C language programs using concepts such as dynamic memory allocation and number representation, and most particularly, pointers. So you're going to hear me allude to the topic of pointers many times in this class. With respect to C programming, pointers are the main difficulty that you have to overcome when coming to C from a more semantically inelegant language, shall we say. Pointers will be a new concept. They are related to the concept of aliases, if you remember that from 1MP3, but I know that those of you who came from engineering or math may not have heard of the concept of aliasing in Python. Did you guys cover aliasing in Python? No? Okay. Not really? Yeah. So, that's fine. The whole purpose of the class is to learn stuff, so. We're going to explore the stack and heap memory models. We're going to test, benchmark, profile, and debug computer programs using a suite of tools specifically oriented to C programming. We're going to document computer programs with comments, literate programming, and tools such as Doxygen. Specifically, Doxygen. We're going to learn how to use Doxygen. Create makefiles to compile programs for you. As we're going to see, compiling programs in a Unix-like environment is not as simple as clicking a button on a GUI. So a lot of you probably have an attachment to one GUI or another. The expectation in this class is that you learn how to do everything from the command line, and that you learn how to use the command line tools. We're going to do things for ourselves in this class. We're not going to rely on fancy interfaces to do stuff in the background and we have no idea what's going on. We are going to learn what compilation means, how to perform it, and how to automate it ourselves using Unix's inbuilt features. I often say to the class that Unix is the original C programming IDE. And we'll get into the fact that that's actually historically accurate. So, pipes and filters. Pipes and filters are a way of connecting the output of one program to the input of another. It's one of the things that gives Unix its overwhelming power. So, we're going to learn how to do that. Using modern revision control tools to manipulate and change computer programs. Revision control is so important that everything you submit will be submitted through GitHub, with the possible exception of the exam. I haven't written the exam yet, so I don't know. We will learn shell scripting. Shell scripting, you can think of it as a sub-programming language whose specific domain of applicability is running other programs. So we're going to see, from a command line, all of the commands that you enter into a command line can be collected up into what are called shell scripts. And those shell scripts can contain loops, and they can contain if statements, and all of the fun stuff that you recognize from regular programming. But the thing that you're operating on is not so much variables and data structures as programs themselves. So it's a bit like meta-programming. And of course, we will learn how to use SSH, which is Secure Shell Client. It's a way, it's a secure shell, SSH, secure shell. It's a way of remotely logging into other computers. So we're going to learn all of these things in 7 weeks, so buckle your seat belts, folks. So, evaluation. 40% of this class's marks come from the labs, 30% from 2 assignments, and 30% from the final exam. The labs are as follows, on the dates as given. The expectation with the labs, you should be thinking of labs in the physics or chemistry lab sense. No post-lab write-up. You're expected to reach various checkpoints and have accomplished certain tasks by the end of the lab period. And you will be graded by the end of the lab period accordingly. So everything is done within the lab period. Right? And it's 4 hours, so there should be more than enough time. Particularly for the first lab, because it's kind of short, but that's okay. Because it's basics. Lab topics. Unix basics, the Unix file system, version control using Git, shell scripting, benchmarking and profiling, environments and libraries, testing and makefiles, continuous integration testing, documentation using Doxygen, pipes, filters, and regular expressions. So, one important point to note, if you see Git, that is essentially the same thing as GitHub. GitHub is a what we call a fork of Git. So they took Git and they've done some of their own things to it to make it kind of uniquely theirs, but fundamentally GitHub is compatible with any other Git repository that you might create, so you can think of them as being interchangeable. Don't be afraid of the words. That's what I'm trying to impress upon you. So, the assignments. The assignments will be on C programming. The release dates for all of those are in the course timeline, which is fine. Assignments will be graded using automatic grading software. Assignment materials will be submitted through GitHub. The assignments will include instructions for submission. Your final examination will occur at the end of the semester and will be cumulative. The exam will be held in person. So, this is a class where, roughly speaking, half of the material that we cover is going to be Unix-based. The other half of the material that we cover is going to be C and C programming. So, if you take a look at the way that the grades are distributed, let's say, we've got 40% you're being graded on Unix, that's the labs. 30% you're being graded on C, that's the assignments. And then my intention is to take the exam and split it right down the middle. so that half of it is Unix and half of it is C programming. So it actually comes out to like 55-45 in favor of Unix, but I think that's, you know, I'm not worried about that, and I don't think you should be either, you know. It's kind of, I don't know why you would be worried about that, unless you really hated C programming. But if you really hate C programming, this probably isn't the class for you anyways. So, extension and late submission policy. Invoking an MSAF for either an assignment or a laboratory exercise results in a 3-day extension for the assignment, or the assessment. So, if you MSAF a lab, you'll get 3 days to complete that lab on your own time. Otherwise, you will be expected to complete it in lab. Right? None of these lab exercises require lab equipment. You will be able to perform all of these labs on your own computers. But that's how the policy is being laid out this semester. Assignment extensions should be, you know, you should be relatively familiar with that type of setup by now. You guys should also know the mechanism by which you submit them. If you want to defer the examination, then the standard university policy on deferred examinations is applicable in that case. And, you know, let's just say, for the sake of argument, that in the second week of this course, you fall down the stairs and you break your leg and you need an MSAF. And you get it. And let's just say, you know, in week 5, you fall down the stairs again and break your other leg and need another MSAF. But, you know, talk to either us or the department. They've been very reasonable about giving people secondary accommodations should that be necessary. I expect that will be tightened up pretty soon in the fall semester, so, you know, maybe take advantage of it while you can. But, you know, I don't know why people ask me this, but yes, if the school gives you an MSAF, of course we will honor it. So, you know. I don't know, is that a thing where like people, like professors just ignore the MSAFs? I don't know. Anyway, so, course timeline. The last day of classes is August 6th. These are the topics that we will be covering and the order in which we will be covering them. You can see that with, except for like one exception, where I have to introduce version control first, so that you guys are set up and know what you're talking about for next week. Roughly speaking, Mondays we'll be talking Unix, and Wednesdays we will be talking C programming. Assignment 1 is assigned in week 3, assignment 2 is assigned in week 5, and is due July 18th and August 3rd respectively. Yeah. I might move the due date up an hour. It's supposed to be the beginning of class, so on the Monday. But anyway. So, this course does not have a required textbook. If you would like some reference, I recommend See How to Program by Paul Hart and Harvey Deedle, the Deedle book. Doesn't really matter what edition you get. In this one, various editions have various like extra add-on things, like the 8th edition also has something on C++ programming, which, you know, C++ is a very useful language, so if you want to pick up the 8th edition, I would recommend it. That's the copy that I have, but, and that's the one I'm recommending here, but, yeah, so that's for the C programming stuff. For the Unix/Linux stuff, it carries its own reference manual. So anywhere you have a Unix command prompt, you also have access to the textbook. because the textbook is the man pages, which we'll get into. Well, I might as well show you now. So this is a terminal. You will come to love the terminal. You will hate it until you come around to loving it. My object with this course is that you should have what's it called? Stockholm syndrome for the terminal by the end of it. So, you enter commands like ls, which lists the contents of a directory, right? I think I can blow this up a little bit. There we go. Lists the contents of a directory. To access the man page or the manual page for any Linux/Unix command, I'm just probably going to say Linux because it's too much work to say Linux/Unix. You type man and then you type the name of the command. And then you read the page. And it gives you all of the options. It tells you what it does. It's very, very useful. Overall, the spirit of Linux is read the damn manual. And this is also something that I've told the TAs to expect of you guys as well. If you're asking us questions that you could easily have answered for yourself by reading the damn manual, then you're going to be told, did you read the manual? All right? What we're going to try to teach you guys is how to find the information for yourselves, because that's a way more valuable skill than simply, this is the kind of stuff where, you're never going to be able to memorize all of the options that, any even moderately, any command that you use, maybe, a couple of times a month, you're not going to remember all the options for it. So, learning how to learn is a very important aspect of this course. So, good. That being said, we are here to assist you, and if you are stuck, then we will provide assistance. We're not trying to throw you into the lake. However, if you find yourself in the lake and you are drowning in the lake, the first question will be, did you try using that ring buoy that's floating right next to you? Have you tried grabbing at that? Primary means of assistance. The TAs in lab are there for the purpose of answering your questions during lab procedures. They'll do a brief introduction to the lab the day of the lab, and then sort of let you guys follow the procedure of your own volition. The labs are designed to be leading you through an exercise, right? And I'd like to think that they are self-contained and self-explanatory, but obviously, you may have questions, and the TAs are there to help you with that. If you require assistance on an assignment, that's primarily what the Discord server is for. Also, any memes that you wish to post may be posted there. Some of you may have taken 1MD3 with me when I was using Piazza, and this is the replacement for that. Oh my god. Jeez. What the heck, man? There we go. What a hassle. Good. So, brief note on academic integrity. Do not cheat. I have been just completely flooded with cases of academic dishonesty this year for whatever reason. So like between my winter and fall offerings of 1MD3, we've processed around 200 cases of academic dishonesty. And that constitutes like a third of the class, little more than a third of the class in the winter semester actually. And let's just say we had a really high conviction rate. One might even say that like the overwhelming majority of the people we caught for plagiarism got either first or second offenses. So some of those cases are still pending, in fact. Particularly the second offenses, because they take much longer to process, because it's like a, like an actual court with an arbitrator, and you have like rules of evidence, and you have to have a hearing, and all of this kind of stuff, and the lawyers can get involved. If you want a lawyer involved, you can get a lawyer involved. But yeah, so don't cheat. We will catch you, and we will penalize you appropriately. And please just don't, please. We're still trying to clear out the paperwork from like the last 2 semesters. We really don't need any more cases. So if you could just not cheat, that would be great. Thank you. Aside from that, we've just got various boilerplate things. Expectations of student conduct, you are expected to conduct, etc., etc. Yeah. Oh, online participation disclaimer. So in this class, we're going to be using GitHub. GitHub is a third-party it's a third-party company. It's actually owned by Microsoft. They bought it out. So if you don't want Bill Gates to have all of your assignments, then I guess we can set up a GitLab for you or something, but don't anybody actually do that because it's a pain in the butt. So, anyway, any questions about that before we start talking about some real nuts and bolts material?
How about your cats?
How about my cats?
Yeah.
They're doing fine, thank you. I don't have any pictures. Sorry. There is one thing that I need to let you guys know about before we go much further. I'm not going to be here in the 3rd week of this course. I'm going to pre-record the lectures and give them to you ahead of time. I'm going to be in Romania presenting a paper at a conference, so I'm not going to be here, obviously, and it's a sufficient time difference that it's problematic, so I'm just going to pre-record the lectures and then you guys can have them. But yeah, the labs will still be running and the TAs will not be in Romania, so they'll be here, so you can talk to them. But yeah, and it's only for the 1 week, so yeah. Yes. Also, I'm defending my PhD thesis 1 week from today. So that's probably going to occupy a certain amount of my time on next Monday. Good. So, right. So, any questions? I know I already asked that, but all right. So, topic 1, shell basics. We're going to start from the very beginning with a brief history of computation. So, it all started back in the 1950s. Although the science of computation is older than this, the first commercially available computer was released in 1951. It was known as Leo. In the beginning, computers were very large, requiring entire rooms and sometimes entire buildings for their housing. Here you can see banks of what would have been at the time vacuum tubes being wired through floor access panels to various terminals. This is how computers used to be back in the 50s. The moon mission was accomplished using computers of this nature. Semiconductors. The semiconductor transistor, which was invented in the late 40s, is possibly the most important invention of the 20th century and possibly human history, period. A little bit biased, but you know. Some people think it's flight. No. Semiconductors. So, what a semiconductor is it's a little tiny piece of silicon that exhibits both the ability to insulate and conduct electrical current depending on the electric field that it's exposed to, right? So, by using electricity, you can set up an electric field that either permits or does not permit the flow of electrons through a semiconductor substrate, right? What this effectively means is that you can create a switch. You can have one electrical signal control whether or not another one flows, right? What that allows you to do is logic. From the individual switch transistor level, you can build up logic gates, logic circuits. When you hear me talk about AND gates and OR gates, this is like what most people think of as the working, it's like the working level of electronics design if you're sort of sub-processor level. So semiconductors started off and they were reasonably large, right? But the thing that was amazing about semiconductor technology was its degree of miniaturizability. So in the 50s, you would have one transistor occupying about this much space. By the 60s, you could fit 16 transistors into the same space. By the 70s, you were talking 4,500. By the 80s, 300,000 approximately. By the 90s, 3 million. By the 2000s, about 600 million. And in the early 2010s, 8 billion transistors in the same surface area, right? It really is true when they say that, like, your pocket calculator contains more computing power than was used to send people to the moon. Like, that is an actual true fact. So this had an effect on the history and development of computing, right? Prior to about this point right here, you could not fit enough transistors. Like, transistors were sufficiently difficult to work with that vacuum tubes were still better. So the big room-sized computers were still very popular. Once you start hitting like the very early 70s, let's say between 68 and 72, transistors surpass vacuum tube technologies, other sort of competing processor technologies, in their degree of miniaturization and their degree of reducing the expense of the machine. As such, you see a literal explosion of what is termed the microcomputer. At the time, this was to distinguish them from the ones that were the size of rooms. Question?
Oh, is that Apple one? You went to the 70s?
I'd have to look it up, but yeah, we're talking about the same. And
personal computer.
Yeah, that's more like toward the early 80s. So what we're talking, like the era we're talking about, sort of in the 68 to 72 range, This is when computers existed, but operating systems, roughly speaking, did not. This is the period during which the first real operating systems were produced. So Apple having an operating system was derived from these earlier efforts. But we've got slides on it. So anyway, I just want to I want you to appreciate this, because this was completely unpredicted. If you look at, for example, science fiction of the 1950s, you can talk about science fiction as being science fiction authors are attempting to predict the future, right? Most of them, even the big ones, completely missed this. The idea that you would be able to have one of these things, and be able to run video games on it. It's this Asimov was writing about people in the very far future still using slide rules. So
Is that called Galaxy Base or the book name? I just don't know.
It's the Foundation series I'm talking about.
Yeah.
So, so around the time of the 1970s, an explosion in computer manufacturing occurred, with different vendors having very different processor architectures. So what happened? Transistors became cheap. Everybody started trying to make processors. Programs written at this time, most notably using Fortran, COBOL, and Lisp, were not generally portable between machine architectures. So you would have, say, 20 different manufacturers of computer CPUs. A program written for one CPU was not compatible to a program written for another CPU. And the reason was they were running directly on top of the processor, and in a lot of cases, these programs were being written in assembly code. You guys know what assembly code is? Put your hand up if you don't. Okay, so assembly code is a programming language written in the direct instructions which are made available by the CPU. So what is a CPU? A CPU is a circuit which implements operations, right? It implements operations in electronic circuitry, and it operates on memory cells which are adjacent to the CPU, right? You have the working memory of the CPU, it loads information, it processes information, it puts it back. That's the what we call the von Neumann architecture. So, what was going on, different chips had different instructions. They would often be implementing the same types of instructions, right? They would all be doing addition, multiplication, subtraction, etc. But crucially, the instruction codes would be different, right? So if you had coded up a program with instruction codes for one processor, they would not be compatible with other processors. What we needed is a layer in between. So, a lack of strong standardization meant that many vendors, included languages. Another problem that was going on. Let's say you had Fortran for some processor X and Fortran for some processor Y. The Fortran compiler in the two cases would have different feature sets. And what you really, really want to avoid is languages that have different dialects for different processors. Basically, if you take program A, you should be able to run it on as many computers as you want. That's the goal, right? So, this all changed in 1972 with the development of the C programming language by Dennis Ritchie, blessed be his name, at Bell Laboratories, the holy mecca of computer programming. Because C was strongly standardized, C programs could be ported across participating computer architectures with no compatibility issues. So, this is how C works, right? You have all of these different computer architectures. Each one of them does a version of the C compiler, but the input language is strictly restricted so that it's the same input language each time, right? That way, from the programmer's perspective, you can write one program, and all you have to do is compile it on each of these individual architectures rather than rewrite the whole program. This is a quantum leap forward in computing, because it meant basically, like think about the degree to which your modern computing device interacts with other computing devices, right? Like your phone is talking to cell towers, and it's talking to Wi-Fi routers, and it's talking to other phones, and it's talking like through Bluetooth, it's talking to Bluetooth devices. Like there's a lot of interconnectivity that's going on, right? This was the first step towards the interconnected world that we now live in. C was originally developed for writing utilities for the Unix operating system. Unix predates C, but only by a couple of years. So, Unix, the Uniplexed Information and Computing Service, where the C and the S are made into an X, because of course they are. So, Unix, developed by the same guys who developed C, at the same laboratory, right? Unix was originally written in assembly code, but after the development of C, the Bell Labs gang re-implemented the Unix kernel in C, and it has remained in C ever since. Basically, what happened? These guys in Bell Labs were sort of visiting around, saw someone else's implementation of an operating system, like an experimental implementation of an operating system. I forget where it was, but I think it was called Multics, something like that. Essentially, they took all of the good ideas and implemented them as Unix, threw in a bunch of ideas themselves. And so they wrote all of this in assembly code. Once they had an operating system that worked, they were like, man, is it a pain in the butt writing programs for this in assembly code? We should have a programming language. So they implemented the C language. They designed and implemented the C language, right? They then took all of their, or a fair amount of the utilities they had written for the Unix operating system, re-implemented them in their new language. And C is the language, has been the language of Unix and Linux ever since. It is the core language of the operating system. And Unix has been extremely influential on the development of computer operating systems. So, due to its low cost and high portability, especially to low cost hardware, Unix has been was widely adopted by academic institutions, and from there the world. So basically they did a really smart, they did the Facebook thing, right? They said, okay, university, we'll give this to you for free. You can try it out, And then the universities were like, well, if we have this thing for free, obviously we're going to use it for all of our students. And then students came to expect Unix operating systems in industry. Boom, Unix becomes almost a universal operating system within a few short years. It was very exciting to be a computer scientist in the 70s. So the reason that Unix was had such high portability was because of the C compiler. You remember how I was talking, like all you have to do is write a C compiler for some architecture and you can compile C programs? All you needed was a C compiler on a particular architecture and you could install Linux. So that's how it got in. So Linux featured some key innovations over previous operating systems, including the ones they ripped off, which are still very much used today. For example, a hierarchical file system with arbitrarily nested subdirectories. So you know how, like, computers have like a file folder system when you're accessing files on the hard drive? Linux did that. Universalization of almost all file formats as new line delimited plain text. So prior to Unix, whether a file was encoded in ASCII or whether it was encoded in binary code, you know, most things were encoded in binary. Unix decided, no, it should be readable by humans. So they took all of the stuff that was encoded in binary, took a little bit more memory to do so, but they encoded it as characters and strings, and, you know, that way people can actually read the stuff and work with it, and it was much, much easier. Much easier, like, you know, the theme of this section is like, how is it that we don't have to program in assembly anymore? And this is the answer, right? Number 3, a pervasive philosophy of modularity and code reuse. The establishment of a set of cultural norms for software development practice. These people did not just establish the sort of operational functions of the discipline, they established the culture, the very culture of software engineering and software development. Any questions about any of that so far? Cool. So, this is, like, I'm going to zoom in. Right. So, this is the Unix family tree. We have the development of Unix, right? After this, we have major branches splitting off as people were like, wow, this is a really great operating system, I want to make a version of it, right? One of the primary branches that split off of Unix was called BSD. But you can see that that the initial development of Linux resulted in a plethora of different dialects of Linux. Some of the notable ones being OpenBSD, Solaris, and you know, shall we say, Mac OS X. So, how many people here are Mac users? Congratulations, you are already running a Unix-based operating system. So, when I say, you know, open up a terminal and do this, you guys already have that ability natively in your operating system. So, yeah. Windows users, you have to do a little more work, unfortunately. But, you know, you also brought a Windows computer to a Linux class, so it's your fault, really. Linux is a Unix-like operating system. It was developed in the early 90s by a man by the name of Linus Torvalds, who we're going to talk about a little bit. It's Unix-based, not Unix itself, but it's, you know, looking at enough of Unix's homework that, you know, the same commands in Unix are going to work in Linux most of the time, that sort of thing. Particularly, you know, operating system doesn't matter as much as the shell, as we're going to get into. But any questions about this? Incidentally, within Linux alone, there's something like, you know, several thousand different sub-distributions of Linux. Good. So maybe we should talk about what you need for this course then. So it is my expectation in this course that you perform all of the work that you're going to do in either a Linux operating system specifically, Or, you know, you can actually do most of it on a Mac in using the Bash shell that Mac provides. It's not that different from the one that Linux provides. However, if you're in Mac, some of the commands will be different, and things like the way the Unix file system is laid out will not be the case, right? Or the Linux file system. So some things are Linux specific, other things will not be. But in general, with Macs, you have, you know, most of the functionality that you need for the labs. If you're a Windows user, recent editions of Windows have what's called the Windows Subsystem for Linux. This is good, but in the same way that Macs are not exactly a replacement for a Linux. The Windows Subsystem for Linux is also not an exact substitute for actually having Linux. So one of the things that we do in this class is we provide a server which you guys can log into and access an actual hard Linux, it's just Linux, right? The server is Linux. So, you know, I would certainly recommend installing Windows Subsystem for Linux if you have a version of Windows that can have it. But we're also going to teach you, even by the end of this lecture, how to SSH into a remote server which provides everything that you need. It has all of the programs installed, and you can use that. You know, if you're really adventurous, you can get an old laptop and install a Linux distribution on it. It's very useful to have gone through the installation process. You learn a lot from it. And I can recommend some distributions to you guys if you're interested as well, which you probably are because you're in the class. But you have a question?
I got a Linux virtual machine that would be fine.
Yeah, virtual machine would be fine too. Yeah. Question?
Would you recommend dual booting?
So the problem with dual booting is that you should always do that on a fresh computer. So this is what happens when you dual boot, right? You take your hard drive and you split it down the middle. Half of your hard drive becomes, or remains Windows, and half of your hard drive becomes Linux, right? Your Windows machine will think it's lost half its hard drive. Like it has no ability to view that other stuff, and if it does view it, it'll view it as an external drive, kind of like a CD. Right? The problem is that you have no control over what portion of the hard drive your files are stored on. Right? So, if you have a lot of, you know, if you have your collection of video game save files, for example, and that just happens to be stored on the portion of your hard drive that you are creating a Linux distribution from, you will lose all your save files. Right? And any other interesting or useful information you may want to preserve as well. Which is why, when you have an absolutely fresh operating system that you've put nothing on, not even any programs, right? There's nothing to be lost, right? Like in theory, you could dual boot your machine if you perform the most thorough backup that has ever existed. Right? Possible. But my recommendation is to just, no. Don't do that. Another alternative is like if you have a laptop, for example, that supports multiple hard drive slots and you haven't used one of the hard drive slots, you can get a new hard drive, plug that in, put Linux on that. That would be another way of doing that without losing any of your existing data. But yeah, don't, please, everybody in the room, do not suffer, you know, apocalyptic data loss because I told you to install Linux, okay? Did you have a comment?
Oh yeah, no, I was just going to recommend what you said, because that's what I did. I was in a second hard drive.
Yeah, yeah, absolutely. Not everybody's got a slot for it. It's like more common on gaming laptops, right? Yeah. Any other questions? Okay. Basically, your homework this week is to figure out how to access a bash prompt. So, let's talk about operating systems. So, choosing an operating system. Do you fear technology? Yes. Is your daddy rich? Yes. Then you're a Mac user. Otherwise, you are a Chrome user. Do you fear technology? No. Do you care about freedom or privacy? No. Then you are a Windows user. Otherwise, do you have a life? Yes. Then you are using Ubuntu, Debian, or Fedora. No, you're using Arch, Gentoo, or whatever that thing is. So, not all Linux distributions are created equal. Some expect you to manually compile your kernel, such as these guys. Others provide scripts that do that. There are some Unix operating systems, such as the installation of Linux Mint that I'm running on my laptop right now, that are so user-friendly as to be almost confusable, shall we say, with a more, commercial operating system. You can run something like Ubuntu or Mint or that other one it's popped up. I keep forgetting what the distro is, but it's become more popular than Mint and Ubuntu. No, not Debian. Debian's like old as balls. It's like something like that. Yeah. Manjaro. Yeah, I think so. Yeah. Which I'll pronounce like that because I'm an Englishman. That's but yeah. So some of these things are really quite user friendly, to the point where you probably wouldn't miss anything from Mac or Windows. Like everything is possible in them. They have this very nice user interface, which is fine, Yeah, personally, in Linux we recognize a distinction between the operating system distribution, like Ubuntu or Mint or Fedora or Debian, and the desktop environment, which is a separate program which is running on top of the operating system. So in this case, I'm using Mint/Cinnamon because, how could you not have Mint Cinnamon, right? Other popular ones include GNOME, and that's GNOME. It's Gnoblin as well. And also KDE is a popular desktop environment. So, what the bloomin' heck is an operating system? An operating system provides a collection of services to user applications, allowing them to run on a computer system's hardware. The operating system is that which sits between the bare metal of the CPU and your game of solitaire. So, user applications are anything from internet browsers to word processors to video games. The API provides system libraries and other utilities via system calls. API stands for Application Programming Interface. What we mean by that most of the time is a set of classes and functions which expose their public members to be able to be called by other programs. You get, like, API is a very popular concept in software engineering. Like, for example, you can get data out of Google Maps by using the Google Maps API, connecting to the API in programming code, and you can get information from the Google Maps servers. This is how Pokemon Go works. So, the So the API is a interface between user applications and the lower level operating system concerns. The lowest level operating system programs are known as the kernel. It's the hard nugget at the center, right? It's the kernel. The kernel has all kinds of things like, how is your computer communicating with its keyboard, right? How are you sending information to the monitor? What does print mean and do? These types of things. That's kernel level stuff. In Unix/Linux, the kernel is primarily written in C. So that's because C is fast. C is a very fast language because it's very simple and doesn't help you at all. It costs time and energy to help poor programmers program poorly. C does not help poor programmers, although poor programmers will still program poorly. So, so the operating system includes a kernel which manages access to memory. That's both permanent and impermanent memory, read-only memory, and random access memory. It controls access to the CPU, input and output handling, and access to hardware and software resources, like printers, right? All of the nuts and bolts type stuff, right? The kernel controls when your fan gets turned on and stuff like that. You can actually, in Linux, you can turn your computer's fan on and off and turn it up and down if you know where the setting is. Most operating systems use kernels written in C because C is fast. Even inferior operating systems like Windows have a kernel that's written in C. You couldn't have because these are the most basic operations that the computer performs, it must be able to perform them as quickly as possible because they're being requested, in some cases maybe 10 to 100,000 times a second. So it's got to be fast. Linux. This is Tux, the Linux penguin. He's the mascot of the Linux operating system and the Linux family of operating systems. Linux is a family of free operating systems, so you have no excuse. It doesn't even cost money. Unix was free until 1984, when AT&T divested itself of Bell Labs. Unix then became proprietary software because whoever picked, I think it might have been, who was it that picked up Bell Labs? Might have been Sun Microsystems, I'm not sure. But anyway, whoever got them, they were like, ooh, this operating system is very popular and I'm sure we could make some money on it. And they tried. And that led to the creation of the GNU project. And the GNU General Public License in 1989. So basically, a bunch of programmer hacktivists decided, no, I'm used to a free operating system, goddammit, and I'm going to continue to have a free operating system. So they were like, we will make our own operating system. We can rebuild him. We have the technology. Basically, this was an intellectual revolution in programming because this was the inception of the open source movement. How many people have heard of open source software? A fair number of you. How many of you haven't? A couple of you, yeah. So open source is it's a different take on intellectual property. So this whole time, up to the inception of the open source movement, how do you want to say? Software was a commercial entity, right? It was proprietary. Copying another company's code could get you in, sue your pants off, right? Basically, software started off with the environment of copyright and patents, which largely exists for any other type of information medium, right? Same rules as movies and that type of thing. The open source movement decided to create essentially a copyright license, wherein the owner of the copyright releases that copyright, kind of like how the guy who invented insulin released the patents, right? So open source software, or incidentally, open source software is not necessarily free, but what characterizes it as open source is that the source code itself is visible to anyone, right? The source is open. Prior to this, the source code itself was a jealously guarded secret, and what was distributed was compiled versions of software in most cases. So, essentially, because it was open source, and anybody who was sufficiently interested could contribute to the project, this led to an explosion of new operating systems deriving from the GNU project. One of which became extremely popular, the Linux kernel, which was written in 1991 by Linus Torvalds at the University of Helsinki. Today, Linux has the largest install base of any operating system, although only about 2% of personal computers run it. Anybody care to hazard a guess how Linux can simultaneously be the most popular operating system and the least popular in personal computers? Yes?
Servers?
Servers, yes. Most servers run Linux, which is a good reason to learn it. But there's another one. There's like an elephant in the room. It's in everybody's pockets. The Android operating system is Linux-based. So, yep. So that's where you get it. Yes. Incidentally, if you're wondering where the name Linux comes from, it is Linus Unix. He named it after himself. So there you go. Also invented Git. So there you go. In Linux distributions, command line interfaces are still commonly used. You may look at a command line interface and think, oh, look how antiquated that looks like. It's like, my God, the 80s called, they want their GUI back, But no. There is still a reason to use command lines among highly skilled computer users. Command lines have a higher skill cap than GUI, graphical user interfaces, right? So you can get more work done more quickly at a command line interface if you know what you're doing than you can with like Windows and its, namesake Windows. Bash, the bash shell, is a very common command line interface in Unix-like environments. Bash stands for the Born Again shell, BASH. And also maybe for the puns, I don't know. But anyway, so this is how you access bash in the various operating systems. In Windows, the Windows subsystem for Linux allows Windows 10 and higher users to access a bash prompt. On Macintosh computers, open up a terminal, and enter the command bash. So the shell so bash is a shell, right? A shell wrapping the operating system. So if we go back here, right? Hardware, kernel, shell, application, right? The shell provides programs using the kernel and supports the execution of application software. So it's an interface, basically. So, and if you're using Linux and you have to ask how to get bash, then I can't help you. This course will require you to have ready access to a bash prompt. Your homework this week is to get your computer set up so that you have access to a bash prompt. Again, there will be some Linux-specific things that you will require an actual Linux operating system for, but a great deal of it, especially the introductory stuff, like the Lab 1 stuff in particular, you don't have to actually be in Linux, although you do for the Lab number 2, because it's the Unix file system, and unless you're in a Unix-like system, you don't have the Unix file system, and it's talking about Linux anyway. But anyway, any questions about that? Pardon me. You guys having fun yet? So, accessing Linux from older Windows computers. We have set up a server for you to log into if the options on the previous slide don't work for you. Remote servers are accessed using Secure Shell Protocol, SSH. On Windows, it is common to use a Secure Shell client such as Putty. There are other ones. It doesn't really matter which one you use, but this one is, sufficient to our purposes, shall we say. You can get that. You can get Putty at this link. Download the slides, get the link. The department has set up the server for the class to use this semester. For more information on how to access it, check the resources section of course content on Avenue. There is a set of instructions there for you to follow, which will allow you to access the Pascal server. Always remember to log out when you're finished. Incidentally, in this class, when you see a word that's like in teletype text, that's what this type of font looks like, that's normally a command or a function or something programming related. So if you're going through the slides with a highlighter, highlight that because it's command. So, bash commands. Almost all Unix and Unix-like systems support a comprehensive set of bash commands. So you can go to Wikipedia to get the full list. There is a lot of them. Bash commands are extremely versatile. The output of one bash command can be made the input of another using pipes and filters. This allows you to use a large number of simple programs to perform really ridiculous operations, like find and replace a specific word in all files with a particular file extension within a subdirectory or your entire operating system. That is one line in Linux. That's just one example. And you guys are going to learn you guys will know how to do that by the end of this class. Bash commands can be collected into scripts and executed as units. This is an absolutely essential abstraction function when it comes to command line interfaces. This is like kind of the whole point. You can execute like repeated sets of commands by collecting them into scripts and then executing the script rather than having to retype all of the commands each time. Bash commands can be invoked from programs written in C or in Python. So you can, from your Python or C program, access bash commands. There's a function for it, right? All of these topics will be covered in this course. Except for the Python bit, because we're not talking about Python, except to make fun of it. So, let's talk about the directory structure. In Linux, the directory structure is hierarchical. Incidentally, they are called directories, not files or folders. That is Windows' contamination of the nomenclature. So, directories may contain files and subdirectories forming a tree. Do you guys remember what trees are? Good. Anybody not know what a tree is? Good. Excellent. Wonderful. I love teaching a second semester class. So, in Bash, commands are executed within the working or active directory. So, if you imagine your operating system as being this great big hierarchy of files and directories, one directory in particular for every shell session, for every shell session that you have open, there's one folder in all of that hierarchy that's labeled as the active directory. Commands are considered to take place inside of the active working directory. You change the active directory using the cd or change directory command. So, for example, and this is like our first actual Unix. So, ls and cd are extremely important skills to get down. So let's say I want to find the directory in which I'm keeping the files for this class. All right? Change directory to teaching. Change directory to 1xc3. There we go. And there we go. I'm now in the active working directory for this course. Normally, it shows you what directory you're in right here, but it can get long, so I removed it because, By the way, Nick is my username because that's my name, and the beast is what I call my computer. So, Nick is logged into the beast. So there you go. To get up a level in the directory hierarchy, very simple, cd ... That returns you to the level above the level you're currently in. And just ... is a way of referencing the current directory. It's normally implied, but sometimes you'll need to include it. So cd ... leaves you in the same directory that you already are. Oh yeah, no, I'm sorry. What I did here was I removed where it tells you the whole, it still tells you what directory you're in, it's just, I removed the bit where it tells you the whole, normally it tells you the whole structure up to the point that you are, and I removed it because it gets too long. But you guys will learn how to do that in lab as well. So, good. Ordinarily in Linux, blue is folders, green is executables. And I think purple is, purple is image files, or I think maybe binary files more generally, but yeah. Any questions about any of that? Cool. So, here is a list of actual batch commands. Let's see what they do. So, let's just go to 1xc3 and let's make summer. There we go. Make directory. Okay. All right. I was about to go too far. So I'm currently in the summer 2022 directory. I want to make a folder for examples. The command that creates a new directory. See how pernicious the Windowsization of everything is? If you want to create a directory, the command is make directory, mkdir, make directory, examples. I can then cd into that, ls, there's nothing in it, make directory, topic 1, cd into that, boom. So, one thing that you'll need if you're to do anything here is you'll also need access to a text editor. My personal preference is forget it. I have the privilege of one that's in a window because I'm running Linux natively. You may be required to use something like nano. So nano, myfile.txt. This is a text editor in the command line, or within the terminal. This is generally speaking called the terminal. You know, I can say something like, the rain in Spain falls mainly on the poor. Save, there we go. Nano is pretty good because it gives you the applicable commands and options at the bottom of the pane for quick reference. So it's like a lot easier to use than something like Emacs, which doesn't. This is what Emacs looks like. Some people really, really, really like Emacs. Emacs is the text editor that thinks it's an operating system. But you don't have to use Emacs. You can if you want to. Emacs is a cool thing to learn, but you know, whatever. The one that I use most of the time, just by default, is Get-it, which you've probably seen me do in 1MD3 many times. So there we go. Text editors. Doesn't matter which one you use, so long as you know how to use it. So, cat displays contents of file. CP copies file to another file. myFile.text, myFile.to.text. There we go. You can see I now have both of those in the directory. And if I cat myFile2.text, I get the contents of the file are the same as they were because I copied the file. That's how it works. ls lists directory contents. As, you know, I've already said, I've shown you what man does. Man cat. There you go. Not to be confused with Catman. So you can see all of these things have lots of options, right? The way that you generally provide options to a Unix command is you use the hyphen character and then a set of letters denoting options. So for example, ls, L, it doesn't just give me the names of the things in the file, or names of the thing in the directory. It gives me what their permissions are and what their date of last modification was. It's a more detailed view. LSL. If I perform LSA, that also displays hidden files. Generally speaking, in Linux, anything that's got a period before the name of it is hidden, right? So, I know you can't see it because it's like, I know, there you go. So, hidden folders in the current folder include this, which is a reference to the same folder, and this, which is the folder above this one in the file system. They're hidden, but they're there. That's why you can use them, right? So, you know, it's not that ... is kind of mysteriously linked to go up a file, like go up a directory, that type of an operation. You are literally referencing a link to the previous file, and that's that thing right there. Make sense? Everything makes sense in Linux. You just have to, you know, you have to find the sense in it. It's like a religion that way. Good. Make directory we did. PS is a list of all processes. So, you know, if I have any actively running things, PS will tell me. PWD lists the full path to the working directory. You know what? I'm going to swap these two because I said I was going to try to avoid having important information lost over there. There we go. There we go. All right. So, from the root of my operating system, home/next/teaching/1xc3/summer2022/example/topic1, full working directory. Incidentally, there is a difference here between what's known as relative and absolute addressing, right? In absolute addressing, that is the address relative to the very top level of the operating system. Relative addressing is addressing relative to the current working directory, right? So, if I were to say, home/nic/teaching/1xc3/summer2022, and I had that as an absolute address, given that my current working directory is this one, if I do cd ... that's the relative address to the same directory. Normally, it's easier to use relative addressing. Incidentally, using CD, you can chain together multiple directories by using the // character. So ls ... That allows you to view what the contents of the folder are, up the hierarchy. If you provide ls with a path, it'll allow you to move around and view things that you view the contents of folders you're not in. But anyway, so cd ... you can see takes me to the same directory. cd /home/nic/ those are dots, nic/teaching/1xc3/summer2022, you can see it brings me to the same place. I know I'm throwing a lot at you guys right now. Are there any questions? You guys will have to be able to do this with some degree of facility by the end of this class. Examples, oh gosh, topic, there we go, back to our directory. If we want to move a file, move means change its name, right? And this can also be used to move it between directories. It's simply mv myfile2.txt to myfile3.txt. And there you go. It just changes the name, right? You can also use this to move things in and out of directories. rm is the most powerful, it's the most powerful command in Linux. It removes files and also folders. So myfile.txt removes it. Generally speaking, rm does not have an undo. Once you delete with rm, it is deleted permanently. Unless your operating system puts it in the trash bin. Incidentally, I'm going to show you how to nuke your computer. Sudo rm r/. Yeah, that will destroy your computer. But you have to enter a password first. So, sudo is an invocation of superuser. Superuser is the elevate, it's roughly equivalent to Windows's administrator status. You know how to, in order to install a program, you have to become administrator in Windows. They'll have that little click-through box. This is what sudo does, roughly speaking, except Linux is better. rm is the destruction command. The R option means destroy recursively, including folders. And this is the top level of the operating system. This command, if executed, will destroy the computer. It will delete the operating system and everything contained within it, including all of your files. And you can do that in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters. So, an uncomfortable silence has fallen upon the room. Yeah, Linux is not messing around. It is very, if you don't know what you're doing with Linux, you can easily destroy your computer irrecoverably and have to reinstall it. So, back it up. Back it up, back it up, back it up, back it up, always back it up. Actually, this is what, one of the reasons we're so persnickety about teaching you guys how to use repos so early is basically what a GitHub, making a GitHub repository allows you to do is it allows you to have a cloud backup of a Unix directory and everything inside of it, as long as the files aren't over a certain size. So, so it's, you know, there are ways of getting your data back so long as you've been careful to keep it, you know, backed up and that sort of thing. But yeah, you can totally just blow your entire operating system out of the water with 12 characters if you're feeling sufficiently malevolent that day. This is the same kind of philosophy that exists in the C programming language as well. It is absolutely possible to shoot yourself in the foot. Both Linux, Unix, and C assume that you're being sufficiently careful with what you're doing as to not destroy your computer. No warranty is provided. Read the manual. Basically. Any questions about that? Incidentally, rmdir removes directories in the same way. And grep we're going to talk about towards the end of the course, but what that does is you can search file contents with, yeah. Like, for example, I'll show you a quick example of grep. Grep RA, find me all instances where the word Linux is used. There you go. This only works because the files are being stored in plain text. But this is everywhere in all of the files that constitute this course that the word Linux is being used. And you saw how quickly I could pull that up, eh? Cool. So, how are we doing for time? Oh, we still got 15 minutes. We can get this done in 15 minutes. So, I'd like to talk for a bit with you guys about network protocols. This is not a class on networking, but it's useful to know some basics. Well, you know, it's useful to know some basics in general, I suppose. So, secure shell protocol. Whenever you get a little number here, that means that this is code. So, and anytime you get the little $sign, that's the bash prompt. So this is a bash command, right? So SSH, username at server URL address.com. So, for example, the Pascal server, you would include the URL of the Pascal server here, and whatever your MAC ID is here, right? So, the Secure Shell protocol is a network protocol for secure remote login over insecure networks, such as the internet. Pardon me. Did you guys know that there's also such a thing as intranet? Yeah. Like, for example, the military has an intranet that does not communicate with the exterior internet. Anyway, a network protocol is an agreed-upon format for information transmission. Anything but military-grade intranet should be considered insecure, and even then. It's kind of funny. My wife's in the military, actually, and she's told me that if you take one of the military computers and like put any random USB into that computer, you get arrested by the NPs come hunt you down and they arrest you. And they throw you in military prison for data insecurity. Or I guess maybe just for a little while, because you know it's only USB. But that's actually like legitimately how like information breaches occur. Like, oh, question or comment?
This practice actually started just after Edward Snowden leaked all the U.S. governance.
Yeah.
Configurations.
Yeah, because if you're putting by the way, if any of you have not watched the movie Snowden, you should watch it, because it's all about all this kind of stuff, and maybe like after having done even a couple of weeks in this course, you'll have a much better appreciation for like what the heck's going on in that movie. But yeah, so if you put a USB into a military computer, you might be downloading, you know, stuff from that computer, and that would be espionage. So there you go. Also, it's entirely possible that, like, this is another like vector of attack that occasionally is done. Like somebody will leave a USB key lying on the ground outside of the FBI building, and like some FBI employee will be like, oh look, a USB key, I wonder who this belongs to, and then they put it into a computer to see the files, to see who it belongs to. Viral attack! Boom! Insertion vector. Ta-da! So anyway, in short, you, the client, open a shell on a remote server. So it's the same thing as this terminal that I've been showing you on my computer, except the terminal is running on someone else's computer, and you are sending the commands over the internet. This is the way that Putty accesses insert server name. I apologize for the characters. It gives you just a little nice little GUI for entering the connection details. So the difference between Putty and this SSH command, you will be required to provide the same information both times. It's just this one you put it into a little wizard, this one you do it all from command line. Like, if this is a secure connection, it will require a password, and it'll like prompt you for one. Make sense? Good. So, here's your ooey gooey gooey. This is the Putty configuration tool. The point of this course is for you to gain computer skills. The most important computer skill is knowing when and how to look things up. When in doubt, consult the documentation. So I'm not going to go through how to do the configuration. You guys have to figure it out. Read the documentation. And use the source, Luke. So, other common network protocols include Ethernet, Internet Protocol IP, Transmission Control Protocol, Hypertext Transfer Protocol, Dynamic Host Configuration Protocol. You'll notice, if you know anything about networking, you'll probably have heard a few of these before. Minimally, you should have heard of HTTP because it starts every bloody URL that you've probably used. Incidentally, you know what HTTPS stands for? Yes?
I think it's secure.
Yeah, the S stands for secure. It's a slightly more secure version. Basically, any website you use at this point in the year of our Lord 2022 should be using HTTPS by now. If not, you probably need to consider which websites you visit. Anyway, network protocols typically define the construction of data packets, which are transferred via the network. In general, data packets consist of a header followed by some data. So you can think of a transmission as being a series of ones and zeros that are sent over a line, right? Sent over some kind of communication medium, be that, you know, radio waves in the case of Wi-Fi, or be that, you know, tiny little wires in the case of Ethernet. You have a packet, right? You have begin transmission, you have the data, you have end transmission. These things generally have a header on the packet that tells computers receiving the packet who the packet is intended for, right? Which computer is this packet supposed to be headed at? The header may contain different information depending on the protocol, such as the size of the packet, the source and destination of that packet, and security features like checksums to see that your packet hasn't been interfered with. Incidentally, when you send a packet, some computer or person intercepts that packet, changes the values, and then sends it on. This is what's known as a man-in-the-middle attack. So, this is what the header looks like for Internet Protocol version 6, which is, you know, I wouldn't say a majority, but a great deal of the information that constitutes the Internet is passed in IP version 6. So, you know, you've got things like the version number, traffic class, flux identification, data length, next header, like a bunch of stuff that doesn't, like, we wouldn't know because it's like internet specific stuff, but most particularly, where it came from and where it's going, encoded in every single packet. So, you know, if you're ever thinking that you're, you know, if you're ever thinking that, like, you know, oh, I'm looking at this thing on the internet that I really would not, I would prefer if my mother didn't know I was looking at it. Every packet that transmitted to your computer, every request you made and every packet has the address of your computer in it. So, you know, just because you've enabled, you know, privacy browser doesn't mean that the fundamental settings, like the structure of the internet itself, doesn't know exactly who you are and what you're requesting. So, you know, just keep that in mind. In general, the exact construction of data packets isn't something you'll need to worry about unless you're a network specialist or an electrical engineer. It's just useful to know that this is what's going on, right? So, and last slide comic, which is like almost right on time. Thank you for calling the Black Hat support line, your first source for Linux support. How may I assist? Anyway, you guys can read the comic. I don't have to read the comic to you. Any questions? Are you guys excited to learn computing? Maybe keep it running so that if there's anybody, like, we've got another 5 minutes if anybody has any questions.
I have a question.
Okay.
So we do have to use Putty. Like, that's a separate thing than the SSH, or is that the same thing?
What Putty is it's a program that implements SSH. You won't be required to use the SSH command if you're using Putty. It assumes that's what you're doing. That's the purpose of the client.
So you don't need to use it. You can just directly SSH through your terminal or whatever.
Yes.
Okay.
If you're on a Mac, then you can just SSH in. You don't have,
Okay.
like, Putty is only really for people with older Windows machines.
Okay.
That don't have WSL. Question?
So in other words, if we are not able to install the Linux system on our laptop to do the C program language coding, we can use Putty to access the server of the McMaster, the cloud server of McMaster as a
Backup.
yeah.
Yeah, absolutely. Yeah. Incidentally, I do not want any of you programming in C in VS Code. We're going to be using Linux this semester. You're going to learn how to do things properly. You have a question?
Sorry, what if you have a newer Windows machine, do you still need Putty?
Well, you don't really need Putty except maybe in a couple of circumstances where, like in Lab 2, one of the things that you're supposed to do is copy certain files out of the Linux operating system into some local directories, which you have to be on a Linux machine to be doing, right? They just simply don't exist on Windows. But what the Windows subsystem for Linux does is it provides you, like all of the bash commands that I did on the board for during this lecture, you will be able to do with the Windows subsystem for Linux, right? It's just, you know, it's not Linux, yeah. It does a very good impression of Linux, but it's not Linux, and at some point you're going to actually have to have Linux. Also, I'm not sure which C compiler it hooks up to on Windows. So one of the things, okay, so we haven't really talked about C yet, but you know, this may be, this is actually pretty important, so I would like everybody to pay attention to this, please. There are several C compilers, right? The one that I expect you to use is GCC, the GNU Compiler Collection, right? It also is a C++ compiler. Windows has their own version, the Windows C compiler. It is not compliant with the C specification. While most things would probably be fine, particularly at the level we're doing things in this class, right? There are differences between Windows, the version of C that runs on Windows, and the version that runs in Linux. And that, like, an error you get in Windows might not be a problem in GCC and vice versa. The same is true with Macs. Some Macs may be running a C compiler called Clang, which is done by IBM. C-Lang, Clang. Clang tends to be a little more restrictive with its errors. Like some things that GCC considers warnings, Clang considers to be errors, and some things Clang considers to be warnings are errors in GCC. So you may not be able to compile a program that you wrote using Clang with GCC. So my fervent hope is that everybody in this room will check to make sure it compiles with GCC before you submit it. Okay? No matter where you wrote it. I don't care where you write it, just make sure that it's GCC compatible when you submit it. Okay? All right, any other questions? Yes, sir.
How do you check that it compiles in GCC?
Oh, in yours? Yeah, I have, like, you just have to double check that, right? You know? But yeah, it might be different for different people's computers.
And how do you check that?
Oh, GCC-V for version. Like, what they do, right, they're very sneaky. They're very sneaky, because they, like, if you enter the GCC command, they'll run Clang instead in the background. But if you ask for the version number, it'll give you a Clang version number instead of a GCC version number. So that's how you can check. Yeah. Good. Any other questions? These are good questions. I like that everybody's in this class at the moment. I hope that you guys continue to come to class. In the spring semester, my 1MD3 class got down to like 3 to 4 students to actually attending lecture by the end of it. So I'd like you guys to actually come to class. Since you guys have to come to class for the afternoon anyways, I hope it's not too much to ask for you to come to the lectures too. But, anyway. Yes? If there are no further questions, then I think we're done for today. Oh, I have a question.
When is the first lab?
It'll be Monday of next week.
Wait, not today.
Not today, no.
So you can just go home after this?
Sorry, for which?
So can you just go home after this?
I mean, if you want to sit in the lab room with no TA teaching you, that's your prerogative. I
That
can't
sounds
control
awesome.
you, but,
That sounds awesome. We'll do that.
I mean, yeah. I don't know if the doors are open. That might be the issue. You know,
do you have a crowbar I can borrow?
not on me. Not on me. I'd have to go home. But, okay. See you Wednesday, folks.
If I can wake up before